Okay, so this is what I'll talk about, heat transport in low-dimensional systems. So I'll mostly talk about one-dimensional systems. So in this lecture, what I'll try to do is I'll basically try to motivate and like what are the interesting questions, and so why study this problem, right? Heat conduction doesn't seem very exciting just like that, but I'll try to convince you that there are really many exciting questions and unsolved puzzles in this simple sounding problem. Okay, so so what is heat so basically we are looking at heat conduction. So you know that heat transfer is like how does energy go from like some region with like hot temperature to low temperature. And we know that transfer can take place in various ways. And so what are the mechanisms? You can have like conduction, and you can have convection, and then we have radiation. Right, so imagine like you have some beaker full of water, and so this is made of some material, let's say some metal, and then we heat it. So let's say we put like a hot plate out here. So this is at some very high temperature, maybe 300 degrees Celsius or something. And then, this is very hot energy, this is hot, and things outside are cold initially. So what happens to the energy, right? How does it flow? So what we know is that, this vessel, this container will get hot after some time because it's a heat conduction. So heat will get, it will conduct along the container and it gets hot. Then the other things that happen is heat is also getting conducted in this fluid. But it also, maybe there, at some point there might be flows inside the fluid, so that's convection. So conduction usually means there's no flow, mass flow. Convection means actually it's carried by some flow of the fluid. So you can imagine inside there might be both conduction and convection. You can ask which is more important. And of course then this guy is also, this is in contact with air. So this is also losing out heat to the environment, and this is both by radiation and also convection, right? So some heat will go in because the air is kind of in contact with this and it carries energy. And then of course there's just direct radiation, which is you don't need any medium, it's just electromagnetic radiation, right? So these are the different ways you conduct heat. We will just focus on conduction, and mostly in like in just solids. Okay. Okay, so what is the typical setup you can think of? So let's say you take a solid, and so this is some experiment many of us do in our undergrad labs, and you take like a bar of a metal or something, and then put it one end at some very hot temperature. I call it T left, and this at T right. Right. So this could be steam, and there you could put ice, and then what you do is you ask what happens, right? So if you, so initially let's say this rod is at room temperature, so it's all constant temperature everywhere. But once you bring it in contact, then what you expect is that if you put a thermometer anywhere, you'll measure some local temperature which is different along the length of the rod. So okay, so basically. Okay, so eventually at long times, system reaches a steady state. Okay, so I'm assuming that somehow you maintain this temperature is constant, right, at the left and right ends. Then inside it will reach a steady state, and steady state means it's a steady state where there's a temperature profile. So t is a function of x. So x is the distance along this, along the. So this is origin, and this is the full system size is L. So x goes from 0 to L. Okay, so you'll get at if you put thermometer at various places, you'll get temperature, constant temperature. You'll get some temperature profile. Okay, and the other thing we know is that there's a heat current flowing. Okay, and let's call this J of x. And so this is current density. So it is the amount of energy flowing across this chain per unit area per unit time. Right? So it's like watts per meter square. So that's the heat current, okay. And so there's energy current and then there's some temperature profile. So basically you can ask what does the temperature profile look like, and what you expect is if the temperature difference is kind of small, TL minus TR is small, then typically you expect that you should get some linear temperature profile like that. So this is T of x as a function of x, 0 to L. So you get a temperature profile. So there's a gradient in temperature, and what we know is that what you expect is that okay, so what you expect is that the current density should depend on the temperature gradient, right? That's the simple. If there's no gradient, no current. If there's a gradient, it should be proportional to the gradient. So it's proportional to the temperature gradient, and the proportionality constant is called the thermal conductivity, kappa. So that's the thermal conductivity of the system. Okay, yeah. Right now I didn't say it could be either due to electrons, phonons, it could be anything, and whatever it is you expect Fourier's, this is, okay, so this is called Fourier's law, you expect that this is what should be true. I didn't talk about the microscopic mechanism, it's just like right now it's just a macroscopic phenomenological law. Okay, so this is called Fourier's law. Which was written by Fourier in around 1820, I think around something around this time. Okay, so this is basically it says that the current density is proportional to gradient in temperature, and this is called the thermal conductivity. So this in higher dimensions you write as. Okay, and this is like locally you measure the current density is proportional to the local gradient in temperature. Okay, so but I just stick to one dimensions, it's easier to say, and afterwards I'll only talk about one dimensions. Okay, so so usually this thermal conductivity is supposed to be a property of the material, and you just like given the material you say either it's you might have a high thermal conductivity, low, it's just a number, right? Okay, now. And you can see the dimensions are some watts per Kelvin per meter. Okay, now okay, so now the other thing you can do is given this solid, what we're interested in is, okay, so let's say what is the energy density at some local place, and the energy density, so energy is a conserved quantity, so so let's say epsilon x at time t is the okay, so energy per unit volume or energy per unit length in one dimension at time t. So at any region, I can just ask how much energy is there, right? Now, since energy is conserved and it's conserved locally, it should satisfy a continuity equation. So we expect something like del TE. Okay, so this is an exact statement. I mean, energy is conserved, so it has to satisfy some equation like this. Okay, whatever energy goes out has to go out locally. Okay, so okay, so now if I use this and Fourier's law, what do I get? So I can plug in J out here, and also we note that I can write the. So this is del T del xt. I can write in terms of the temperature by just saying that this is del E by. Okay, so the energy density should depend on the temperature, and so I just write del E del T and then del T del small t, right? Okay, so this is of course the specific heat per unit volume of the system. So let's say this is specific heat in times del Tt. Okay, so and the right hand side, what I get is basically, so if I use this equation, what I get is specific heat times del T, T equals to del X kappa del xt. And let's assume, just for simplicity, that the thermal conductivity is independent of temperature. Then I can bring out the kappa outside, and then basically what I get is okay, so now you can see that this looks like the diffusion equation, and this thing has dimensions of diffusion constant, thermal conductivity divided by specific heat. Okay, so this has dimensions of diffusion constant meters square per second. Okay, and so this is the heat diffusion equation. Okay, so basically Fourier's law implies that heat transfer is a diffusive process, and so the rough idea is that whatever is carrying the heat is kind of doing a random walk, maybe, right? That's how you get the diffusion. Okay. Okay, so now, I mean, so I'll just say some, like given Fourier's law, what are the things that you would expect to see in experiment? Okay, some of the things, ways you can use the diffusion equation, okay. So, okay, and so when you study heat conduction, you can do it in two kind of setups. One is what I'll call an open system setup. Which means the kind of setup I just talked about, like your system is in contact with, yeah. See, energy density, if we assume like it's local equilibrium, and it should depend only on like temperature and maybe other properties like pressure and all, but in the simplest situation, I just imagine it's depending on temperature, right? I mean, energy density, it's a thermodynamic quantity. It should depend on the whatever thermodynamic properties, right? So it doesn't depend on kappa. I mean, it's just an equilibrium property. Okay, so the open system setup is when the system is in contact with reservoirs, and so that's what I talked about. Okay, and given this, what kind of things can you say from Fourier's law and the diffusion equation? So what we can say, for example, is in the steady state. So steady state is when the things don't. So initially, when you put this rod, things will change, right? The temperature is evolving with time, but it reaches a steady state. So in the steady state, what we see is that from Fourier's law, you can see that this current must be independent of position. So the current has to be constant everywhere, right? I mean, so there's a constant, the current here and current here must be the same. So this is independent of x. And so you can integrate this equation. And if I assume that kappa is independent of temperature, then the solution of this is just given by sorry. So what I'm saying is, see, this is the basic equation. Now, at long times, this temperature doesn't change with time, right? So this left-hand side is 0, which means that del x of this is the current. So this is 0. So this must be a constant, right? So it's just constant, independent of x. Right, so that's all I'm saying. So J is, in general, it might depend on x, but in steady state, it doesn't depend on here, right? It's true anywhere anywhere you measure the current, you'll find the same value of current. Yeah, but it's the same current must go, right? Otherwise, it would heat up. If you have a large current going here and a small current going here, it will heat up, right? This region. But I'm saying it's in a steady state. Things are not changing, which means the current here and here should be the same. Everywhere it should be the same current.
So, including the point 0 and L.
Yeah, everywhere it's the same current going. Right? Otherwise, things somewhere it would heat up. Okay, so this is in steady state. Okay, so the steady state, I'll just call it, there's a standard notation, non-equilibrium steady state, NESS, okay, non-equilibrium steady state. I'll just use this notation. So right now I'm talking about the steady state properties. And if you solve this equation, then given T left and T right, what you find is that the temperature profile is given by just T left plus, this is easy to, it's a linear equation, you just integrate and you get this. And also the heat current is given by right, okay, so these are two sort of very simple consequences. You get a linear temperature profile which matches at the two ends, and you get a current which is just given by delta T divided by L. Okay, yeah. No, I'm assuming finite L. Because in your lab you have a finite L, right? You don't have an infinite L. Otherwise, it will take infinite time to reach a steady state. You need a finite L. But finite but large L, yeah. Yeah, I just solved this equation for a finite rod, right? X goes from 0 to L. I just integrate this. There's no, it's completely straightforward. Yeah. This one. I think it's, okay, so sorry, I didn't define what is delta T. So delta T is TL minus TR. And you can see that if you put x equal to 0, it matches with the left boundary. If you put x equal to L, sorry, you're right. Yeah, minus, okay, so it has to match the both boundaries, okay. Okay, so this is the temperature profile, and that's the A. Okay, then you can also ask other sorts of questions. For example, you can ask, like initially I just put this rod at constant temperature, right? So you can ask transient questions. So this is x and this is t. So at time t equal to 0, the left end is at some hot temperature, and then I started my, this is t right, this is t left, right? So let's say the rod was at room temperature, at some temperature t room, and at the boundaries there's some jump, and then the system is led to evolve, right? So eventually we know that this temperature is going to change, and eventually it's going to become like that, right? So you can ask, how does this change take place? And again, that you can just solve this, the diffusion equation. So it's like an initial value boundary condition problem. Which I won't discuss now, but you can. It's easy to solve this equation with these boundary conditions and see how this evolution takes place. Okay, so this will later come back to this question about. We'll find that for like the kind of systems we look at, it's a different equation, and then solving this equation would gives some surprising features. Okay, so this is another question you can ask, and in many experiments, like what people do is, for example, you can put temperatures which are actually oscillating in time, and again you can explore like what is this, how does this solution of this equation behave, and you can extract a lot of information about transport in this system. Okay, so but the basic EA is for in usual diffusive systems. This is the basic equation with which you can extract a lot of information about transport. Okay, so these are some questions you can ask in the steady state in the open system setup. And other thing that you can look at is what is called the closed or isolated system setup. Okay, so these are open system. And okay, so so in this kind of setup, what you do is, let's say you have again you take a rod or something which is at room temperature, so it's in equilibrium at some temperature, and then what you can do is you can just dump a lot of energy at some local region, right? So let's say you just put in a lot of energy, maybe like in experiment, there are experiments where you shine a like very localized laser beam, right? So you dump in a lot of energy here, and then you can ask how does this energy spread, right? So that again is given by this diffusion equation. So if you say that let's say the temperature is let's say the room temperature plus some theta of xt, where theta of xt is the initial like pulse that you put in here, you can ask how does this spread, and of course it again satisfies the diffusion equation. Yeah. Yeah. Open system, there's no dissipation in the bulk, so I'm assuming so I can ignore radiation and stuff like that. So there's no dissipation into the, like in the bulk of the chain. At the boundaries, of course, there's dissipation in the sense that it's exchanging energy with the reservoirs, right? Only at the reservoirs, yeah, nothing at inside is completely conservative, right? And here I'm assuming that there's no reservoirs and it's kind of an infinite system. Okay, so if you solve this equation again, let's say when you put a pulse, it corresponds to putting maybe with some delta function. You solve this equation with delta function initial conditions, and then we know the solution, right? So what is the solution of this equation? Gaussian, right? So that's just the diffusion equation, and if you solve with theta x at then we know that theta of xt okay, so that's just the diffusion propagator, and this constant just determines how much of energy you put in, right? It's not normalized to 1, it just tells you how much energy that you put in the pulse. Okay, so yeah.
That solution has the problem that you get a response at the edge at time t equals 0.
Oh, right, yeah, it has there's no speed, right, yeah. It has infinite speed, that's what you're saying. Yeah. Right, yeah, yeah. So, right, yeah. So, I mean, maybe you have to, yeah, then people put right in this. Right, yeah. So, yeah, but if you look at bulk property, usually it's negligible, right? Those sound peaks. Right, yeah, yeah. Okay, so, okay, yeah. So we'll actually later discuss sound modes and so on. Okay, so this is what happens when you put, and there are actually experiments where the way you measure thermal conductivity, for example, if you want to measure I mean, so what are the ways you measure experimentally? Okay, this is very difficult usually. Like, okay, that's one of the ways you do, but it's not so easy. I mean, one way, like if you, there are experiments, for example, on graphene, and they typically take a graphene sheet, which is, let's say, suspended graphene, and then you just put a laser beam, and then you just look at, you just somehow measure the temperature at this point, and see how does that change with time, right? So if you, so you can see that theta at time 0 t at the origin, it just goes down as 1 by root pi 4 pi dt. Right, so it should decay as 1 by square root of t in 1 dimensions. In 2 dimensions, it would be 1 by t. And that tells you, for example, that it's a diffusive process, and maybe you can somehow extract the diffusion constant and the thermal conductivity, right? So this is one simple way you could, experimentally determine thermal conductivity. Okay, and so one other feature of this solution is that it has a scaling form, which is, you can write it as 1 by square root of t, some function of x by root t. Right, so in this case, this function f of u is just e to the power minus okay, so so it has this particular scaling form. Okay, so this is important to remember. If it's a diffusive system, usually like if you put a pulse, it spreads in this way. Okay, so so this is of course one thing you can also do experimentally. Just put a heat pulse and see how it spreads. And okay, so. Okay, so afterwards we'll see that when we want to study the system from a microscopic point of view, then we will look at these two frameworks, both these frameworks, this open system framework and the closed system framework. And in the closed system framework, I mean, like putting a pulse and then looking at how it spreads is equivalent to like looking at equilibrium correlation functions. Okay, so the idea is that if a system is in equilibrium, there are always some fluctuations all the time, right? So if you measure energy locally, you will find that it fluctuates, okay? And then you can ask, how does this fluctuation relax, okay? And what you expect is that, I mean, the fluctuation should kind of relax in the same way as a extra pulse, okay? So therefore, like if you look at correlation functions, so let's say I look at energy fluctuations. This sort of correlation functions, these correlation functions basically tell me how do spontaneous fluctuations relax in equilibrium, okay? And we expect that, so let's call this some correlation function, which is function of space and time. It should behave in roughly the same way as this object, okay? And this is something that we can like try to compute from theory, like standard theories, okay? So this is something we'll discuss later. When we discuss the microscopic approach. Okay, so far I have talked about like just phenomenological idea of the heat conduction and the Fourier's equation and what you. Okay, so this I'll just do a small historical digression about some like some very early application of Fourier's law, which is kind of very interesting. Okay, so I was just reading and I thought it's good to just discuss this. So, I mean, so one of the earliest application was actually in determining a very fundamental question, like what is the age of the Earth? Okay, so. Okay, so what is the age of Earth? 5, huh? 4 to 5, right? Yeah. So I just looked up Wikipedia. It says 4.54 plus minus 0.04. Okay, I don't know how accurate that is, but at least that's what Wikipedia says. Okay, so now, like, what was the, like, the, so in 1844, Kelvin made a sort of, this was, I think, one of the first, like, quantitative estimates of what is the age of Earth, right? I mean, if you think about it, it's a very hard question. How do you estimate such a thing? Okay, and he used a very simple idea. Actually, this was one of the first, like, sort of nice applications of Fourier's law. So what he said is that, so what is you have to start with a model of how things happen. And his model was, let's assume that the Earth started as a, at some point it started as a hot ball of, like at a very hot ball at some uniform temperature, which is like 6,000 Kelvin. Okay, so yeah, I don't know how, I mean, okay, how you got this number, but somehow you knew that it should be around the temperature of the sun. So, so let's assume this, and then of course it's cooling, and so it cools, and then right now it's no longer a uniform temperature. So what happens if you go down into the Earth, the temperature increases, right? At the surface it's kind of cold, and as you go down and down, it gets hotter. So, at time t equal to 0, the temperature looked like that. So let's say this is a radius versus this is the radius of Earth. So it's 6,000 is temperature, and then it's 0 degrees, right? This is the starting temperature. And after whatever number of years, I mean, so this is age of Earth, we know that now it's not, I mean, there's like, maybe it's hot, it's cold out here and hot in here. And if you plot the temperature as a function of radius, it should, so instead of that, it should probably look something like that. Okay. Right, okay, so to go from here to here, so in Kelvin's model, he assumed that this, I mean, the space is always at 0 degree, okay? So space is 0 degree, and inside it's hot, and so at the boundary, it just reaches to 0 degree, okay? So how do you go from here to here? Of course, what's happening is that, okay, it's losing heat at the boundaries from hot to cold, but inside it must conduct heat, right? So it's like there's rocks and, or not rock, whatever is there, it has some thermal conductivity, so heat has to flow across it, okay? So it's kind of a slow process, and eventually it, right now it looks like something like this, okay? So what we know is that at present, or in Kelvin's time, what was known is that if you go about a kilometer into the Earth, the temperature increases by 30 degrees Celsius, okay? So, so the temperature gradient here is like 30 degree Kelvin per kilometer. Okay, so this is dTdr. Right, this is the temperature gradient at the surface of the Earth. Okay, so now given this information, how can you estimate the age of Earth? Okay, so I mean, of course, you can solve, like you have the diffusion equation, you can solve it with whatever boundary conditions, and then you can see, you get it. But you can do some simple argument, and I'll just tell you this argument about how to get this number, okay? Okay, so okay, so basically it starts like that, and then it's become like that after. So this is at time t equal to 0, and let's say this is at time t after some years, and this is a function of radius, the temperature. Right, okay, so now you can ask, like, diffusion is a kind of a process where the times, like, if you ask, like, how, if you put in some ink, how long does it take to spread, right? We know that r square goes as time. So what we know is that, okay, so for a diffusive process, we know that r square, okay, so in 3 dimensions, it should scale as something like that, right? I mean, that's how, so if you ask what is the size of this this layer, its typical size should be, okay, so let's call this delta r. So this delta r should be should have this scaling, right? So 6dt. So therefore, we can calculate the gradient. Okay, so now what is the gradient? Roughly, what is the gradient? So t divided by delta r. That's the gradient, and that's given by t is just this t naught, which is the 6000 degree Kelvin, and delta r is just root of 6 dt. Okay, so this is equal to dt by dr. Okay, so this is roughly the idea. Okay, so these are all approximate symbols. So if you assume a diffusive process, then you expect that the gradient should change with time in this way. Okay, it's just heuristic estimate. And so then you can ask, I mean, how long does it take? So at very short times, the gradient was very large. And then as with increase in time, the gradient becomes smaller and smaller, right? So the gradient is decreasing. And you can ask, when does the gradient become what is the observed gradient? Okay, so of course the time is okay, so this is what you get, and if you put the present values of dt, dr, and this is 6000, and then diffusion constant for like the Earth. I mean, so this is like if you look at typical diffusivities of like let's say rocks and so on. This is like order of 10 to the minus 6 meters square per second. So that's the typical diffusivity of many materials. And then this you put all the numbers, and what you get is, so this gives you around, okay, so this I said was 30 degrees per Kelvin. This is 6000 and d is this. And then if you just compute this, you get something like 4 into 10 to the power 15 seconds. Okay, and this if you convert to years, it's around 100 million years. Okay, so this was quite amazing because at that time, I mean, people had no idea. I mean, I think like of course everyone had an idea about what like at least people tried to have some idea of how old the Earth. I mean from religion, of course, you have some ideas of how old the Earth should be, which was maybe much smaller. But also it seems the geologists, I mean, somehow they had the idea that the Earth, the life was infinite. Okay, I mean it existed forever. So, I mean, there was a big argument about between geologists and the physicists about like who was correct and so on. Okay, so but so this is just. Okay, but I mean, can anyone think like was this a good calculation? Or can one think of an improvement of, or like what are the possible problems in this calculation? Huh?
Radioactivity.
Okay, so okay, one possible problem is radioactivity. So the Earth, I mean, so it seems like inside the Earth there's a lot of radioactive sources and it produces heat, right? So there's an extra source of heat which we haven't. But what else can one think of? Huh? Sun, okay. Sun. Sun gives some energy, okay. That is actually small because if you, I mean, it's also at same temperature, but it's a small area compared to what it's sending, right? So it's, huh? Radiation. means is the sigma T to the power 4, Stefan Boltzmann, yeah, okay, so that's radiation. Okay, any other problems? Huh? Yeah.
Why does this have to be especially?
Diffusivity, right, yeah, that's also, I mean, yeah, so that's a question. I mean, diffusivity maybe it depends on radius. Okay, so there are all these possibilities, and okay, so around I think 1875 there was I mean one of Kelvin's assistant actually he did did another calculation which was slightly different, and okay, I don't know, this does it make a difference, water and this? I think water is better, right? But anyway, this for this I'll use this and then go back to water. Okay, so so there was this guy called I think, yeah, right, yeah, right, yeah. No, no, so that is of course the sharp cutoff. Of course, I mean, so that model is a bit strange. I mean, why is suddenly 0, right? I mean, space. Okay, so I mean, I think a more accurate statement of the problem would be that I mean, at the boundary, there's a current flux, which should be so something like this, right? I mean, I think. So this is the flux of this is the heat flux at the boundary, and this should really be equal to maybe something like right, yeah. I mean, it should be radiating, right? This could be a possible boundary condition that you should use to solve the equation instead of what Kelvin did. Okay, but this of course is very difficult to solve. Okay, so that's one possibility. I don't know actually how you would solve this equation. But the other thing that this person did, his idea was. Right, yeah. Right, yeah. Right. Right, yeah, yeah, yeah. Right, yeah. Right, yeah. Right, yeah. So that is but this equation, like equating the energy that we get from the sun to the radiation, this will of course give kind of a steady state, and then we find that it's close to what we have right now, right? But if you ask, like during the cooling process, where it was much higher than let's say the temperatures right now, then I think you can ignore the thing coming from the sun. So in the most of the part in the history, you can ignore the energy coming from the sun. And at the later parts, when it's close to steady state, maybe it's important. Okay, but what was this guy's idea? I mean, this John Perry's idea was actually, I mean, the Earth, maybe it's something like this. So his model was like the Earth is really something which has maybe a crust which is like 50 kilometers. And inside it's, I mean, their transport is not really heat conduction, okay, because it's a highly mixed like fluid, I mean, all sorts of turbulence and so on. Here convection is important. So you can assume kind of that it's in a constant temperature, okay, there's no gradient and all. And it's just this region that dominates the, this is like a solid thing, this is around 50 kilometers, and this determines the, this cooling process, okay. So with the same model, I mean, same kind of equation and same boundary condition, 0 degree, and with this extra input, he again recomputed the, and he got a number of like 3 billion. Okay, so which is much better. Okay, so okay, but this is now you can ask like what happens if you really do it properly and take. So now of course we know a lot about the Earth, what is inside, but of course we don't know exactly how this entire process happened, right? I mean, slowly this was solidifying and then growing. You have to put in a lot of more details. But anyway, fine. The main point is that it gives you some idea. It's like it's not at least trillion years, right? It's 3 billion years. It's 100 million years. And so this was a nice use of simple laws. Okay, so this was just a historical digression, and now we get back to the main question, which is now this Fourier's law is a phenomenological law, right? Okay, so can we understand it from complete microscopics, which means starting from, let's say, Newton's equations, can we derive this law? Okay, and I should just say that it's similar to, I mean, for example, I mean, other laws are like Ohm's law. I mean, that's a very similar law, right? I mean, so there you have like maybe charge current is equal to sigma E. Okay, so it's instead of a temperature gradient, you have electric field and you have a thermal conductivity. And so these things like electrical conductivity, heat conductivity, these are called transport coefficients. And okay, so these are all transport properties. Okay, so now, so the main question is how do we okay, which means basically from, okay, so given Hamiltonian of a system, okay, so okay, so this question is how do you compute the transport coefficients? But more fundamentally, you can ask how do you derive the Fourier's law? Okay, so I mean direct derivation. I mean. Okay, so I mean, general comment is that in so given a system, we're interested in some properties like what are known as equilibrium properties, like magnetization, susceptibility, specific heat. These are all equilibrium properties. And in statistical physics, we know that you have Hamiltonian, then you have some prescription due to Boltzmann and Gibbs, which tells you to compute the free energy, and from the free energy, you can compute all sorts of equilibrium properties, right? So the other kind of things, material properties of interest are these transport coefficients, which are kind of non-equilibrium in that it's not at the same temperature, like you have either some driving and then you should look at the response of the system, right? So these are the transport coefficients. And there is some formalism called linear response theory, Green-Kubo formalism, which maybe some of you have heard about, which gives some prescription of how to compute this transport coefficients. Okay, so at some point I'll state there's some results from linear response theory. But still, those are like, so linear response theory is kind of first order perturbation theory about the equilibrium state, okay? So it's still, there are a lot of assumptions going into derivation of linear response, so it's not completely exact. And so we would like a more basic understanding of transport, right? Yeah. Okay, so how would you do that? I mean, so what's the most direct way you can study this question, okay? So so one of the most direct ways to do this is basically, okay, so let's call it a direct verification. Is to, let's say, I take a system with some given Hamiltonian, and to start with, like Deepak said, it's always good to look at the simplest models. So we'll take a one-dimensional system and try to verify if this Fourier's law is true. Okay, so one-dimensional systems means I have a chain of particles which are moving, which just have like x in one dimensions. So okay, so they are moving on the one-dimensional line, and each particle has a position qi, qx, and momentum px. Okay, so I have n particles, 1 to n, and this is described by a Hamiltonian. Okay, so this is the kinetic energy of each particle, and this one is like if there's an external potential which each particle sees, and this is like a nearest neighbor interaction. So I just assume particles interact by some nearest neighbor interaction potential. So this is the Hamiltonian, and and then of course, what are the equations of motion? So equations of motion for the particles is just yeah, so n qx double dot. Okay, so I've just, so this V prime just indicates derivative with respect to the argument. And so, when I take del H by del QX, you can see that QX appears in like with the x plus 1 particle and x minus 1 particle, right? It has it appears in two places in the Hamiltonian. So that's why I get two terms here. And because of this minus, I get here plus and minus. Okay, so this U prime just indicates derivative with respect to the argument. And because here is QX and QX is here, so there's a difference in sign. Okay, so this is the equation of motion for the particles. Now, to study heat conduction, what I should do is I should kind of connect this system to heat reservoirs, right? T left and T right. Okay, so this is if I want to do the open system framework. So I have to connect it to heat baths. And so what is the simplest way I can like put in heat baths? Huh? First, so I have to do something to the dynamics because it's interacting with this thing, and I have to do something, right? So one of the simplest way is, okay, so you have to model the heat bath dynamics in some way. So the first particle sees bath dynamics corresponding to temperature T left, and the right has a different here. So the simplest way to do is use Langevin equations, right? So we know that, okay, so we know that if you have, let's say, I mean, just a single particle, let's consider a single particle in, so there are these experiments where you put a particle, like a colloidal particle in an optical trap, and you ask what is the dynamics, right? So, so then the dynamics is like mv dot equals to minus del v by del q. Then you write, because there's an environment which is the bath, right? The colloidal particle interacts with a fluid or something. So you have interaction terms, which is, there's dissipation, and then there's noise. Okay, so, and the noise is, okay, let's call it T. And so this is called the Langevin equation. And so this entire term is basically like the effect of the entire fluid can be replaced by this simple dynamics, which has a dissipation term and a noise term. Right? And the noise has this important property that, okay, it's completely uncorrelated, it's white noise. So it's uncorrelated in time, but the strength of the noise is given by 2 gamma Okay, so it's uncorrelated in time, and the strength of the noise depends on the dissipation and also on the temperature. Okay, so this is called a fluctuation dissipation statement. And what this dynamics ensures is that, okay, so if you look at the particle following this kind of stochastic dynamics, and for example, if you measure the velocity as a function of time, of course, you'll find that it does it has a stochastic trajectory. But you can compute averages, and you'll find, for example, that V average is 0, but V square average is what? Huh? Yeah, so V square average, you'll find that it's KBT divided by M. Okay, so that's equipartition, right? I mean, it's just that the fact that velocity has equilibrated to thermal equilibrium. Similarly, if you look at the position, and so let's say this is a harmonic trap. So let's say V is equal to half K Q square. Then if you measure Q square, so as a function of time, Q, of course, will look like a stochastic trajectory. But if you take this average, you'll find that this is equal to KBT by the spring constant, right? So this dynamics ensures that the system reaches thermal equilibrium. In fact, if you look at the full probability, you can ask, how does this probability behave? And you can show that it actually, at long times, the system will reach just the Boltzmann distribution. Okay, so in this case, H is just okay. So that's that's the idea of the Langevin dynamics. It basically captures the effect of all the heat reservoir into a simple dynamical equation. Okay, so for our chain, what we'll do is, for this guy, we'll write a Langevin equation corresponding to whatever temperature, and for this guy, we'll write a different Langevin equation with a different temperature, right? So they just have different temperatures. So therefore, these equations are valid for, let's say, x equals to 2, 3, to n minus 1, and for the first guy, I write something like mq1 double dot And for the last guy, okay, okay, so maybe I'll put a 0. You want Q1 minus Q0? Right, yeah, okay, so maybe this, okay, so this is something about boundary conditions, okay. So their particles are 1 to n, but this Q0 and Qn plus 1 I just introduced to put in boundary conditions, okay. So if you have fixed boundary, what are known as fixed boundary conditions, okay, so maybe I should just say, so these boundary conditions are kind of important here, so. Okay, and Q0 and Qn plus 1 are introduced just to fix boundary conditions, okay, so. Okay, so that's just boundary condition. Okay, so afterwards we'll see that sometimes this is kind of plays a crucial role. Okay, so this is dynamics, and the noise, this one, they are uncorrelated with each other, and their correlations are basically. So I've already taken care of the strength, and so this is just delta t minus t prime. Right, okay. So this is the dynamics. Particles in the bulk, they just satisfy Newton's equation. So there's no dissipation, right? Someone asks, is there dissipation? So inside is completely conservative. At the boundary, you have both dissipation, but also you have like energy can come in through noise, right? So it will. So what the boundary bath is trying to do is, it's trying to fix the temperature of this left guy, and the right bath is trying to fix the temperature at the right end. And then it will get into some steady state, and we want to understand in the steady state I mean, we want to check various things to see if Fourier's law can be established. Okay, any other questions? 14 minutes. Yeah.
Could you explain why the longitudinal dynamics is the right way to consider?
Okay, so what I said is that what the Langevin dynamics is that, I mean, see, if, I mean, the Langevin dynamics, I mean, if you have water and you put a colloidal particle, right? What you find is that, I mean, this particle eventually reaches thermal equilibrium, Okay, from whatever initial conditions you ask in the long time, it will reach thermal equilibrium. Okay, and so you want to write so basically it's because it's in an environment, right, thermal environment. And if you want to model it, the simplest way to model it is Langevin dynamics. Okay, so it's this is one thing we know, that the Langevin dynamics ensures that the system will reach thermal equilibrium. Okay, so that's the idea. In fact, you can verify that if the two temperatures are equal, then the system will actually reach the Boltzmann distribution again. Okay, so at both ends you put the same temperature, it will just equilibrate to some constant temperature.
Suppose the two ends have the same temperature.
Right, yeah.
Then usually to reach thermal equilibrium, you need a random force at each site.
No, but they're all connected, right? And they're all connected. They're all connected with each other. So you just need energy at like Langevin dynamics at the end. In the bulk, you don't need a Langevin dynamics. It will go to equilibrium, right? Yeah. Right. So, for example, okay, you can ask how. I mean. Okay, this I'll come to later. I mean, how do you prove that it will reach thermal equilibrium and so on? Okay, so let's maybe, okay, what should I do? Okay, let me first state the questions that we want to understand. Okay, so we have this dynamics and then we let the system evolve, right? So I mean, this is a stochastic system, so the things keep changing with, I mean, they're just randomly evolving. But after some time, you can imagine that initially, let's say all the particles were at rest and you just connected it, then energy will flow in and eventually it will reach some steady state, right? So, so let's see if it's in the steady state, what all can we measure, okay? So what are the things we want to measure if we want to understand Fourier's law? We want to measure the current, energy current that is going through the system, and we want to understand what does the temperature profile look like, right? So those are the simplest things that one can look at. Everyone can read, is it? The size is okay at the end? Okay. Of interest. Okay, so temperature profile. Okay, so for systems in equilibrium, we have some idea of what is temperature, right? And there's some prescription. But one of the things we know is that for a system in equilibrium, there's something called equipartition. And it states that for a system in equilibrium, if you compute, let's say, kinetic energy of any particle, and at the average kinetic energy of any particle, then this is actually equal to kBT, right? So for all particles have the same kinetic energy, average kinetic energy, this is equal to. And also you can measure some other things, okay? So for example, in this model, you can compute something like qx into del h by del qx. Okay, so this is like the force on the particle into its position. Okay, so now you can show that this also has to be equal to kBt. Okay, so this is some sort of a statement of equipartition again, that these things in equilibrium have the same value, and whether you compute it this way, you get kBt. Okay, so in this kind of a framework, what we expect, of course, is that temperature is changes at various places, but I mean, we just define the sorry. No, this is just kBt. Yeah, this is just kBt. Okay, so in the non-equilibrium steady state, we just define local temperature at a point. I mean, so now this is okay. So from now we'll set Boltzmann constant equal to 1. Okay, so it doesn't. So Kb is 1. So temperature is just Px square by m. Okay. So we can still measure this quantity, like local kinetic energy at each site we can measure, and that should give us the local temperature. Okay. Now, what you expect that it's a good temperature only if once you define it this way, it should also reproduce other local properties. So this temperature should also work when you compute other local properties. Okay. So for example, if you now compute this object, it should match with this. Okay, so in equilibrium, you know it has to be true. In a non-equilibrium case, this is not always true. Okay, so in some case, you might find if you so this is just a, like some observable which you can measure in your experiment, right? So you just here you just look at Px square and then do a time average and you get some number, and this similarly this you can do a time average and get some number, and there's no guarantee that this will be equal. Okay, now what you expect is that if a system is in something called local thermal equilibrium, then the temperature is a good variable, and then they should kind of match. Okay, so this is but right now it seems like if a good definition of temperature is just to take this quantity, right? So this is how we'll define temperature locally at a point. So Fourier's law, of course, implies there is local equilibrium and you can define a local temperature. So then this should be a good definition. Okay, so for the purpose of Fourier's law, this is a good definition, and we'll just use this definition. Okay, and then the last thing I want to mention is how do you measure current? Okay, so to measure the current, yeah. These averages are okay, so in the steady state, what you expect is that if you take time average, or you can take an ensemble average, right? And they should be the same. So there's a, just like we had a Boltzmann distribution was the equilibrium ensemble, in the non-equilibrium steady state, we have an ensemble which we don't know. Right, we don't. Typically we can't compute this non-equilibrium probability distribution, but there is, there is one in principle, and we can either use that to compute averages, or we can just do a time average. If you do a simulation, for example, you just do a time average, and they of course will give the same answer, right? So you can think of them either as a time average in steady state or just ensemble average. Okay, so now you want to current. So of course, how do you in general define a current? You have to write a continuity equation, right? So we just write a continuity equation, and maybe I'll just do that and stop. Okay, so basically, Okay, so this of course we all know, right? In quantum mechanics, you have like Schrodinger's equation, and then if you want to define what is the correct current operator, you just write density del T of density, and you find that it has form of divergence of something, and you call that the current, right? So we'll just follow the same procedure, and what we have to do is somehow figure out. Okay, so we have to define a local energy density epsilon x, and once we have that we look at the time evolution, and so somehow it should have the form that the rate of change of this energy should be something flowing in and something flowing out, right? It should have that form. So we'll try to see if we can get that. So first point is to note that we can write the energy as sum over epsilon x. Okay, so so what I did was this is of course just a purely local part, but this is the interaction energy which kind of lives on the bonds, right? So I took kind of half the energy from here and half from here. Okay, so you can do this in various ways. You could have just taken this bond energy and this energy. That also works. I mean, it's kind of you're free to choose what you write for the energy density, but you have to write it in a local form, and you have to make sure that the total Hamiltonian is given by this. Okay. Okay, so this, I mean, half comes because you count it twice, right? On every, when you go to every side, you count it twice, so you need a half here. Okay, so this is the local energy at each particle, and then you just take time derivative. So let's just do this. So if you take time derivative, we get px by m into px dot plus v prime of qx. Okay, so I'll just quickly finish this. Okay, so this is it, and then we use the equations of motion. So here px by m is just qx dot. So let's replace this by qx dot. Okay, and for px dot, let's say we are looking at the bulk particles. So px dot is just this. Right? So if I okay, maybe I won't write the steps, but if you just put px dot equal to this quantity, so just plug in px dot in that equation and just do some cancellations and all. So what you'll get is okay, so that is homework. Okay, this is what you get. Okay, and now if you look at it, you can see that this involves x plus 1, and this is the same thing with x replaced by x minus 1, right? So therefore, this is you can call this as minus j x plus 1, and this is as jx. Okay, so so basically you want epsilon x dot should be minus okay, so I can write it maybe in slightly more way. So maybe j x minus 1 to x. So this is current flowing from x minus 1 to x minus j x to x plus 1. Okay, so you can think of it this way. Okay, so this is like a discrete formulation of, normally you'd get something like del xj, right? This is the continuum yeah, but since we are on a lattice, this is kind of the discrete version of this equation. This is the divergence equation. Okay, and there's a minus sign. So this, okay, so so therefore you identify it like that. So this is the current going from x to x plus 1, and this is the current coming from x minus 1 to x. Okay, so therefore we have an some operator which tells us what is the how to get the current. So jx, so this is the current operator. So jx is just minus minus. Okay. This one? That's plus, yeah. Okay, so so this is the form of the current, right? So this is some function of qx and this is some function of velocities, and this is something we can compute explicitly in a, if you know the steady state, right, or in a numerical calculation. Okay, and so basically in this. So this is particle x, and this is x minus 1, and this is x plus 1. So that object basically gives you the current from x minus 1 to x, okay, average current. Okay, so I just want to say something about the, so if you take the, in the steady state, what you can show is that you can kind of rewrite this equation so that this just has the form u prime qx minus qx minus 1 Okay, so even though there are two terms, you can in the steady state you can rewrite it so that it has just one term. Okay, so I'll prove this in the next class. But I just want to end by saying that this has a very simple physical interpretation. What is this current operator? So basically, what is this object? It's the force on the x particle at x from the x minus 1 particle, right? So it's just force. So you have particle x minus 1 and x, and this is just the force this particle exerts on this, and this is the velocity. So force times velocity is the rate at which this particle does work on this, right? So that should be the energy current. So it's just the rate at which this guy is transferring energy from here to here. So this is a simple physical interpretation. Okay, so these are the things that we can, so we can compute microscopically what is the current, we know the temperature, and now we want to ask, like, can we somehow see that Fourier's law is true, okay? Okay, so the main story will be of these lectures is that in strictly one-dimensional systems, you find that Fourier's law is not valid. And then we'll try to understand what is a good description of such systems, of heat transport in such systems, okay? Okay, so that's, so any questions? So at the, okay, I didn't say, but in the next class we'll discuss the boundary. So of course what happens at the boundary is this energy goes from here to here, and then something is coming from the reservoir, right? So it will be a bit different, the form of, so right now you can imagine this is valid for particles in the bulk. At the boundary you have to be a bit more careful, and you'll find that the rate of change in energy involves current coming from the boundary and then something going to the right. Okay, so we'll write an expression for the this current also, and similarly at the other end. Okay, so we stop.